Welcome. Today, we're diving into a classic mechanics problem from Irodov's collection, number 1.64. Okay, let's get into it. When you first see a problem like this, with all the blocks and pulleys and angles, it can feel a little overwhelming. It looks like there's just a ton going on.
And that's a totally fair question. The secret to these isn't about having a bunch of formulas memorized. It's about having a clear, step-by-step process. And the first step, well, it's not what most people jump to.
Before we even touch a formula, before we even think about F equals ma, let's just take a breath and list out what the problem actually gives us. This simple step keeps us grounded and helps us avoid a lot of silly mistakes down the road. So, what's in our toolkit? We've got the angle of the incline, alpha, which is 30 degrees. We have the ratio of the masses, eta, which is 2/3. And we have the coefficient of friction, nu, at 0.10. And our one and only mission? Find the acceleration of the whole system, which the problem calls w. Sounds straightforward enough? All right, now here it is. This is the single biggest trap in any problem that has friction. Before you write a single equation, you absolutely must figure out which way the system is going to move. Why? Because that friction force always fights against the motion. If you guess the direction wrong, your friction force points the wrong way, and your whole calculation is toast. So, no guessing. We're going to figure it out for sure. The best way to approach this is to think of it like a simple tug of war. We've got forces pulling the system in one direction, and we've got forces pulling it back in the other. We just need to see which team is stronger. So on one side of the rope, we have the weight of mass 2, right? It's trying to pull mass 1 up the incline. On the other side, we've got a team of two forces working together. First, you have a component of mass 1's own weight trying to slide it down the incline, and helping it out is the maximum possible static friction, which is going to resist any attempt to move it up. So how do we actually compare these two sides? Well, the force from mass 2 is just its weight, m2g. The maximum resisting force from mass 1 is that downward gravity component, m1g sine alpha, plus the maximum static friction, which is k times m1g cosine alpha. Now, to see who wins, we just compare m2g to that whole expression. And to make life even easier, we can divide everything by m1g. This boils it down to a really neat comparison. We just need to see if our mass ratio, eta, is bigger than sine alpha plus k cosine alpha. Let's plug in the numbers and see what happens. Our mass ratio, eta, is 2 divided by 3, which is about 0.667. Now for the other team. Sine of 30 degrees is 0.5 plus 0.1 times the cosine of 30 degrees, which gives us a total resisting value of about 0.587. And there you have it. The pull from mass 2 clearly wins. 0.667 is definitely greater than 0.587. This is fantastic news because now we know for a fact that the system is going to move. Mass 2 is going to go down, and it's going to pull mass 1 up the incline. And that means we now know the direction of kinetic friction on mass 1. It has to be pointing down the incline, fighting that upward motion. All the guesswork is gone. Now that we've nailed down the direction of motion, we can confidently move on to the next crucial step, drawing our free body diagrams. This is how we visualize all the forces before we turn them into equations. Okay, let's zoom in on mass m1. We've got the tension from the rope, T, pulling it up the incline. And fighting against that motion, we have two forces both pointing down the incline. That component of gravity, m1g sine alpha, and now the kinetic friction force. Mass m2 is way simpler. It's just a vertical fight, right? We have its weight, m2g pulling straight down, and that same rope tension, T, pulling straight up. All right, our diagrams are set. Now for the really satisfying part, translating those pictures into the language of physics. We're going to apply Newton's second law, F equals ma, to each of our masses. And here are our two equations of motion. For mass m1, let's say up the incline is the positive direction. So the net force is the tension, minus the two forces dragging it back, and that whole thing equals m1w. For mass m2, down is the positive direction of motion, so its net force is its weight minus the tension, which equals m2w. So look at what we've built. We've got a classic system of two equations with two unknowns, that tension T and the acceleration w. Since our goal is the acceleration, it's time to do a little algebra and solve for it. Now, here's a really neat trick that works all the time in these pulley problems. If you just add the two equations together, watch what happens. The plus t in one equation and the minus t in the other, they just cancel each other out completely. It's so convenient. This leaves us with one clean equation where the only thing we don't know is our target, the acceleration, w.
And after a little bit of rearranging, this is what we get, the final general formula for our acceleration. And look how nice that is. It's expressed using only the things the problem gave us in the first place. G, our mass ratio eta, the angle alpha, and that friction coefficient k. Now for the grand finale. We just plug in our numbers, with eta being 2/3, alpha at 30 degrees, and k at 0.10, the math works out perfectly. We find that the acceleration of the whole system is 0.05 times g, the acceleration due to gravity.
And hey, notice something? Our final answer is a positive number. That's not an accident. That's our final little confirmation that all that hard work we did at the very beginning to find the direction was correct. The system is moving exactly the way we predicted it would. It all fits together. So what's the most important thing to take away from all this? It's not the final answer, 0.05 g. Who cares about the number? It's the method. It's the process we used to get there.
This 5-step game plan is a powerhouse that you can use on almost any dynamics problem that gets thrown at you. First, deconstruct the problem. Then, strategize, and that means figuring out the direction of motion before you do anything else. Then, diagram your forces, write your equations, and finally solve the algebra.
See, when you focus on having a solid process like this one, what looks like a really complex challenge just becomes a simple checklist you can follow every time. Thanks for working through this one with me.